let's start. So starting with the first thing, TK, let's try and do both questions. This paper is, what is this paper? This is February, March 2021, paper 5.2. So the first question is about, the first one, it's about zinc reacting with copper sulfate. So it's a typical displacement reaction. And the enthalpy change of this reaction, delta H, he's trying to determine the enthalpy change by adding excess zinc powder to a measured volume of 0.05 mole per dm cube. So he measures 25 cm cube. So the amount of copper sulfate that you have, that's 25 centimeter cube and 0.5 mole per dm cube. So he's adding, at 4 minutes, he adds 3 grams of excess. So there's 3 grams of, remember, excess. So he's adding a lot of zinc to it. And then the reaction starts. So at 4 minutes, TK, this is where the reaction is going to start. And as soon as he adds it, the temperature starts to rise. Use the results table to use the graduations on the thermometer that is used to record these temperature readings. So what do you think is the graduation on the thermometer? Like what's the minimum graduation of this thermometer based on the reading that you see? Is it 1? Is it 0.1? Is it 0.01? What is it? Just a sec. I said this one is it's not 0.1. It's actually it's definitely not 0.1. Reason being the thermometer scale, I think, is like you had 18 and after that you had 19. After 19 you had you probably had 20 and so on, and then it showed a value of 32. So basically it never had a 0.1 graduation. The 0.5 that you see over here, that's basically the value being somewhere, if the value is right between the two values, you're going to call it 19.5. So the graduation, minimum graduation that you have over here, that's 1. Is that clear? Because अगर 0.1 होती ना, then you would have seen 19.1, 19.2, 19.3 or something like that. If you're just seeing half, that means this is not the minimum graduation. It's probably 19 and then all of a sudden it's 20. So anything that's in between, that is going to be taken as 0.5. Draw a label diagram of the apparatus setup at 1 minute. The apparatus setup at 1 minute. So probably a styrofoam cup. And what did we do at 1 minute, by the way? As for 3 minutes, and so I don't think there's a lot happening here. There's just a thermometer that's added. Zinc powder is being added to it. So at 1 minute, we didn't do anything special at 1 minute. So it's how many marks is this? This is just 2 marks. So I guess styrofoam cup with that's about it. The apparatus that is set up at 1 minute. So for this, I would have to check the marking scheme whether this is correct or not. It's a simple, very basic apparatus that is required for this reaction. So just polystyrene cup, we did that. We had to label copper sulfate and the thermometer with bulb clearly within the solution. So freestanding labeled thermometer, and freestanding, you shouldn't be holding it. So probably, so the mistakes were So our mistakes were that because if you're holding it, then you're transferring heat energy to the thermometer. So it's probably, I mean, you could have shown it. Freestanding means they're independent of you. I mean, the bulb, we showed that it's correctly inside the solution. We didn't label copper sulfate, so that's one other thing. So you had to label it in detail. But anyways, the rest was all fine. You had to label this as well, that's your polystyrene cup. And that's your stand. As if the next one. Plot a graph to determine y-axis against time, which is x-axis. Use a cross to plot each plot. So I'm going to plot all the points, which are given below. So before this, so 0, 1, 2, 3, that's 18, 19.5, and then 19. So for the first 3 minutes, 0, 1, and 2 and 3. So it was what? It was 18 and then 3 19.5s. So 18 is somewhere over here. That's what's 18? 18 is, I think, this line. And then it was 19.5. So I think at 0 it was 18. And there were three values for 19.5. There's no value at 4. And then all of a sudden the temperature rises. So 32.5 and 38. So 32.5. 32.5 comes over. Where does it come? 32 point. So that's 31. So that's 32.5. And then you have 38 and then 36. So you have 38 next. That is going to be this one. No, 38 is going to be, that's 36, 37. This is 38. And then the next one is 36. So that's this one. Up at 34 and 33. So you've got 34, which is, this is 31, 32, 34, and then you have the next one, which is 33. And basically it's dropping, okay? So you can, so the temperature change, he's asking for the temperature change in this reaction. Now the curve is, and did he ask us to draw the curve? He's saying extrapolate the cooling curve back to 4 minutes and determine the temperature change. So we've got a cooling curve. This is my 4th minute. This is the point that we need to extrapolate it back to. So that's my cooling curve. And always remember that your temperature change is your initial temperature, which is the starting point, and the extrapolated temperature, which is over here. So that's your delta T, and this is going to give you what? It's going to be 19.5. And this one is going to be 41.5. Okay, so that one is 41.5. So difference where that's what's the difference? Delta T. What are we getting for delta T over here?
$22.
Okay, so delta T comes out to be 22. Okay, so we got a delta T, which is 22. The next thing is he's asking you to use the formula minus MC delta T to determine the enthalpy change of the reaction. The mass is, so So Q is equal to MC delta T. So the mass of the solution is the total volume of the solution. So the total volume of the solution that we have is 25 cm cube. Right at the beginning, that is the amount of solution that we had added over here. So we've got 25 grams in our solution. So this is 25 grams. C is already given, that's 4.18. And the delta T was already calculated, that was 22, and it's an exothermic reaction. So what do we get for Q? As a Q की value आ रही है, that's 2299. Or we can say 23.0. We're getting 23.0 kilojoules. If we round it to 3 significant figures. So heat loss is a major source of error in the results of the experiment. Suggest how the following changes would affect the amount of heat loss at all. Explain your answer in each case. So the first one is the mass of zinc is doubled. What will happen to the heat loss if the mass of zinc is doubled? How would that affect? I just saw you 2.3 here. As a mass of zinc is doubled in the experiment. Would that have any effect on the amount of heat loss?
Would the heat loss be greater?
And why? Remember, zinc is already in excess. Okay, so it's already in excess. So if you if you go back, if you even add more zinc, the reaction or the amount of heat that's going to be produced, it's going to be exactly the same. So the reaction it's going to be the same exact reaction that's going to happen. So adding more mass will have absolutely no effect on the experiment since it's already in excess. So effect on heat loss, no effect. Why? Because it's already in. Okay, and what the concentration of copper sulfate is doubled. The amount of zinc used is still in excess. So if you double the concentration, would there be more reaction or less reaction if I double the concentration of the copper sulfate?
More reaction?
Yeah, there's going to be more reaction, right? Because you got more copper sulfate now. The zinc is already in excess. So there's obviously going to be more reaction. So if you have more reaction, that would now mean that so if there's more reaction, more heat is produced, right? So if there's more heat produced, there's obviously going to be more heat loss, right? I mean, that's basically your explanation for that as well. As the next one, what if we double the volume of copper sulfate? The amount of zinc is still in excess. So if you double the volume, what is going to happen now? Will there be more reaction now? Okay, so there's going to be more reaction, right? Because moles is doubled. Moles is like if you the moles of copper sulfate is either you double concentration, you double the volume, the moles will increase, right? So there's going to be more reaction, more heat is going to be produced. So there's definitely going to be more heat produced. But will there be more heat loss or not? There's obviously more heat being produced. Heat loss kind of remains the same, and there's a reason for that. See, Q is MC delta T, right? So that means forget C. C is the constant, right? So basically delta T is what? It's the amount of energy that's produced over the mass of the solution, right? So the point is that that if the amount of energy doubles, right? And the volume of solution also doubles, which means the mass of the solution also doubles. So what happens to the temperature change? That remains pretty much exactly the same. Like you've got a bigger volume now and there's more heat being produced. But since it's a bigger volume, the temperature rise is not going to be that high. You can remember this, if you double the amount of heat produced, but at the same time, you double the volume as well. Like think of boiling water, right? You're trying to boil water. If there's a smaller volume, and you provide it with a small amount of energy, the temperature rises quickly, right? If you have a bigger volume, the mass doubles, more energy is going to be given to it. The temperature rise would still be the same. So the idea is that if you double the volume of the solution, obviously there's more moles. The amount of heat energy produced would also double, but the temperature change would kind of remain exactly the same. Is this idea clear? This thing?
Yes, sir.
And the heat loss is based on the temperature gradient. So that kind of remains exactly the same as well. So in this case, you clear this, Javier, is this clear, this part? As the next one, to get that question is over. But this thing is an important point. I mean, this specific point is very important that that based on Q is equal to MC delta T. I mean, you should be able to manipulate or analyze Q is equal to MC delta T. Like if I, for example, I double the energy change doubles, and the volume of the solution is halved. So what would be the rise in temperature? It's going to, I mean, you should be able to analyze what's happening. Like if you double the mass and the temperature remains the energy is going to be doubled. Because you should be able to analyze what is the relationship between all these three values. Now, next question, ethane dioic is a white crystalline solid. If in excess of aqueous potassium hydroxide, there's a reaction happening between ethane dioic acid and KOH. And he says that potassium ethane dioate forms, which is also aqueous. If a small amount of potassium hydroxide is added, partial neutralization takes place and not all of the H+1 in the acid are replaced by K+1 ions. So this is the acid. And this is our base. So he's saying that if a small amount of potassium hydroxide is added, not all of the H+1 get neutralized, or so there's partial neutralization. Like if you have H2SO4, maybe just one of the H+1 gets neutralized. So partial neutralization. What he means is this thing. Ethane dioic acid is this acid. Full neutralization is that both of the H+1, they get neutralized and they form a salt with KOH. So K+1 comes and replaces the H+1. Partial neutralization is both of them don't undergo neutralization. One of the H+1 is still intact. It is not neutralized. One of them is neutralized. So instead, in acid salt form, this is known as an acid salt. I mean, the same thing kind of happens with H2SO4 as well. Partial neutralization. Like if you add a small amount of NaOH, maybe just one of the H+1 gets knocked out, and you're still left with H2SO4 minus 1. You add in more NaOH, then the other H+1 also gets knocked out, and you have no more H+1 ions in the salt. So instead, in acid salt forms, the letters A, B, and C represent a ratio of the number of species present in the compound and may not necessarily be whole numbers. The relative numbers of water molecules associated with one formula of the compound is represented by D, whatever that means. So he's saying that a student attempted to determine the values of A, B, C, and D in the sample of an acid salt. So that's your acid salt, which is getting formed. So I don't think there's a lot of things that can happen. That this is ethanoic acid. So maybe there's 1K+1, maybe there's 2K+1. So the student wants to make a 250 cm³ aqueous solution of this salt, solution A. The student adds 1.89 grams into a 100 cm³ beaker. Describe the next steps the student. Now this is something that's very important, how to make solutions. This comes in P5 very, very often. How do you actually make a simple solution? So he's saying describe the next steps a student should take to make solution A containing exactly 1.89 grams of this thing. Give the name and capacity of the apparatus which should be used, and describe how the describe how the student should ensure the volume is exactly 250 cm. Write your answer. So basically you have to make a solution. So the first thing is, you've already done the difficult part, which is, I mean, it's basic steps. They give you, it's a 4-mark, but it's like simple, very basic steps. So you already have 1.89 grams that has been added to a beaker. So you're setting with a beaker, a small beaker, and the beaker, remember, beaker is not a measurement device. So if the beaker is, so you haven't really added anything yet to the beaker. I mean, it's a 100 cm³ beaker where you've added 1.89 grams of this, whatever this is, Ka, HP, C2O4C, whatever this is, C2O4C dot DH2. What's the next step? You're going to add some distilled water into this. So there's this salt that's at the bottom. So add distilled water. And you stir with a stirrer. Until the salt dissolves. So it's eventually going to become a solution. So this thing will eventually turn into a solution. What's the next step? You want to make a 250 cm³ solution that contains 1.89 grams. So what you're going to do next is, you're going to take a volumetric flask which has a volume of, so volumetric flask kind of looks like this. So take a 250 cm³ volumetric flask. Should have a funnel over here. So transfer the solution that you've made to a 250 cm³ volumetric flask. Once that is done, you're going to wash now your beaker is empty. So wash the beaker with some distilled water and throw that into you don't want anything left over here. So you're going to clean the beaker a little bit. So wash the beaker with some distilled water. And you transfer the washing into the volumetric flask. So basically you've cleaned the beaker and thrown everything into the volumetric flask. Now, the volumetric flask is not full because it still needs some water. You need to fill it up with. So basically that's the last thing. So add distilled water to volumetric flask and make it up till the mark, which is the 250 cm3 mark. So add distilled water to volumetric flask and make up to the mark, which is the 250 cm3 mark, and that's it. So basically it's not rocket science, but it's a 4-mark question and it's easy 4 marks. Okay. Is this clear?
Yes, sir.
I said next one is, I said somebody's saying 1D is wrong. Are we sure this is wrong? 4.18 delta T. I said one of the reasons it could be wrong is probably delta T. Let me just check. I said so there's that part is fine. There's nothing wrong with that. We did not read the question fully, this part. Because he wasn't really looking for this, he's looking for the enthalpy of the reaction. I mean, this is fine. I mean, there's nothing wrong with this. This thing is fine. We missed a part, which is that enthalpy change is for 1 mole. Okay, so that's the part that we missed. So we need to actually find out the moles of copper sulfate. Just 1 second. How many moles of copper sulfate do we have? What's 25 into 0.5 divided by 1000? Get that at 25 times 0.0125 moles, right? So basically we did not complete this. So get that minus 0.0125. So this is for minus 0.0, not minus, plus. And that produces, I said that produces 2.3 kilojoules of energy. The ratio, we had to use ratios and then we had to figure out what is the amount of energy that's produced by 1 mole. So what do we get? इस part का किया calculate?
Negative 184.
So you're getting negative 184 for this.
Yes, sir. Yeah.
So negative 184 kilojoules, right? Per mole. Think 184, negative 184. They're saying it's minus 205, but obviously we did not make a proper graph. So you can print it out and make a proper graph, but we are close enough. We got minus 184 with a rough graph. So coming back to this, we were able to make this solution. Now this entire thing, now what he's doing is determine the number of moles of C2O4 ions present. Ethane, so there's a titration that's happening. I think that's happening with C2O4 minus 2 ions with KMnO4. So the student rinses and fills the burette with KMnO4. So the MnO4 is at the top. So he's adding it from the top. And the C2O4 ions are in the flask. So the solution that you made that contains C2O4 ions, that's sitting in the flask at the bottom. And it's going to be added dropwise. Student uses a pipette to transfer 25 cm3. So there's 25 cm3 of this in the flask. The student adds 20 cm3 of sulfuric acid. You need sulfuric acid. There's acid. So I think that's just to acidify it, because you need H plus ions. The conical flask is heated till 80. The student starts adding MnO4 from the top, from the burette, until an endpoint is reached, and there are 3 titration results. When emptying the pipette in step 2, the student touches the surface of the solution in the flask with the tip of the pipette. Suggest why the student does this. Now this is an experimental technique. Why would you're emptying a pipette, right? So why would you I mean, it's just common sense, basically. Why would you touch the surface of the solution? So there's a solution in the conical flask. Take the last drop. I mean, imagine this is the pipette. The last drop is usually just hanging over there. It's sticking to the pipette. So if you carefully touch the surface of the solution, that drop will get attracted to the solution. It will fall into it. So to ensure that all the liquid from the pipette has gone into the solution. So
We
exactly.
can say to maintain accuracy.
हाँ लेकिन वो फिर general हो जाएगा थोड़ा. वो exact बता, so that the last drop in so the pipette is completely empty, ठीक है? And all the 25 cm cube has gone into the solution. How do you measure sulfuric acid? What's the most appropriate? You're supposed to add 20 cm cube. So what is the device that you're going to use to measure sulfuric acid 20 cm cube? And you don't even need to measure an exact amount because you're adding it in excess. So agar quickly add karna, what is the best device for measuring 20 cm cube of sulfuric acid?
Burette.
No, burette is too accurate. It's rough.
Measuring cylinder.
Measuring cylinder. It's an excess. I mean, burette is when you have to exactly measure pinpoint accuracy. When you're just adding 20 cm cube something in excess, a measuring cylinder is fine. You don't have to be that accurate. Suggest why the student starts each titration with an initial burette reading of 0.1. This is important. Why would he not? Remember, imagine this is the burette, right? Now imagine this is the burette. It has KMnO4. He's saying that every time he's starting at 0.1 instead of 0 cm cube, or at least in the first titration, but in each titration. Why does he not fill the burette up till the 0 cm cube mark? Like if you're familiar with practicals, you fill it up till the 0 cm cube mark. Why do you not fill it up till the 0 cm cube mark in this case? Koi idea, any random idea? I mean, it's a completely random thing, by the way, but I'll show you.
Sir, leakage.
नहीं कि वो तो नहीं, मैं दिखा देता हूँ. Let's KMnO4 in burette. Maybe you'll get an idea why it's not good to actually fill it up till the 1 second. So this is how the apparatus probably looks like. Okay, so it's got KMnO4 in the top, right? So somebody said it's exactly. Problem is if it gets filled up till the 0 cm cube mark, maybe they're showing it somewhere. But you'll get an idea. If you fill it up till the 0 cm cube mark, you wouldn't even be able to see the 0 cm cube mark because it's so dark that all the graduations will vanish. So you wouldn't even know where the top is. So it's important not to actually fill it till the top, because then, I mean, you need to see some of the graduations, right? So do you understand? Do you get the idea, right? Even if the last graduation is filled up, then all the graduations are missing then. And you have no idea where the starting point is. Is you clear about this? Is this clear?
Yes.
So remember, dark color, it basically applies to KMnO4. Never fill it up till the 0 cm cube mark. because if that is gone, then you don't see anything. So what is meant by concordant readings? What are titration concordant readings?
सर
You
ये जो आपने KMNO4 वाली बात की है ये कोई और एसिड के लिए भी एप्लीकेबल है?
ये सबसे डार्क कलर वैसे लैब में ना it's KMNO4 ना, तो it's usually applicable. KMNO4 के साथ ना you don't see any readings. So that's why it's not good to actually fill it up till the top. कम से कम एक तो नजर आएगा, ठीक है? तो अच्छा, but is this clear? This one concordant reading पे आ जाओ. What's concordant readings? You keep on doing titration until you get concordant results. What are concordant results? What are the ones that are within 0.1? Readings which have a difference of 0.1, or results which have a difference of 0.1. State the color seen in the mixture in the conical flask at the end point. Remember KMNO4 titrations, it's dark purple, it's purple. As long as it keeps reacting, KMNO4 keeps turning colorless. So initially the flask remains colorless because there's a reaction happening, and whenever a drop goes into the flask, it immediately turns colorless. But जब वो खत्म हो जाएगा, when all the C2O4 is gone, if you add KMNO4, then the KMNO4 would remain purple because it's got nothing to react with. So the end point is when it turns purple. So the flask remains colorless because the KMNO4 is constantly reacting. As soon as the reaction is over, any extra KMNO4 added will remain purple. So it will be colorless to purple. Determine the number of moles of C2O4 ions in 250 cm³ of solution A. Give your answer to 3 significant figures. Did he give us any results? I think results diye. Which ones are concordant results? He actually gave us the average titer. So 24.4 KMNO4 is the concentration of KMNO4 is also given. Can somebody tell me how many moles we have? Like the KMNO4 that you're adding to from the top, that's 24.4 and 0.02. So how many moles do we have?
(4.88 into 10 to the power -3).
So you're getting 4.88 into 10 to the power -3.
-3.
So 2:5. So C2O4 के solution के अंदर moles निकालो. It's 2:5. So find out, divide this by 2 times 5. How many moles of C2O4? 10 to the power -4 है? Divide by 2 times 5. That's कितने आ रहे हैं? That's
Yes, sir. That's actually -4. My bad.
ठीक है. You can say it's 4.88 divided by 2. That's 2.44 times 5. That's going to be what? 1.22. 10 is per minus क्या होगा? It's going to be minus I think 3. Can somebody check this? Is this correct? And those are the moles. Okay. And those are the moles in 25 cm³ of the flask. Okay. So KMNO4 top said that that's in the flask. So that's in the flask over here. And he had specifically asked in the question, what did he ask? He asked 250 mein kitne the? So that's in 25. Like you just use 25 cm³ for titration out of the 250. So in 250, you're going to have 10 times more. So that's going to be 1.22 times 10 to the power -2. Okay, so it's going to be 1.22 times 10 power minus 2, because you found out in 25 cm3 and 250, that's going to be 10 times more. And then finally you have, if you are unable to calculate, forget that. The student then does an acid-based titration of solution A to determine the value of A and B in this thing. Suggest a name of a suitable reagent to use in this titration. So he's saying that he's trying to do an acid-base titration for this thing. So what is a suitable reagent for an acid-base titration? And remember, this was the acid salt, right? So this is the acid, TK, which was partially neutralized. So there was still H+1 left. I mean, there were H+1 ions that were still part of the formula. So this was your acid salt. So you need a base for that. And I think the most suitable base is just NaOH, I guess. TK, that's NaOH. And remember, initially he was talking about this as an acid, that this is what it, so the other thing that we're looking for is a base. The student finds the concentration of H+1 in solution A as 6.1 times 10 power minus 2 for solution A. Use this value in your answer to be 6. Determine the ratio of C and B and to 2 decimal places. Then reduce the value of A in, okay. So basically we figured out C2O4 ions. We figured out its moles, right? We figured out C2O4 ions. So how many ions do we have? 1.22 times 10 power minus 2. We figure that out. And I think that's the, so we still have time, but let's try and do this. Okay, this is a tough one. So we figured out C2O4 ions. Starting with, I think we took 1.89 grams of the salt. And in that 1.89 grams, we made it into a 250 cm3 solution. We figured out that we have 1.22 times 10 to the power minus 2 moles. We figured that out. So we figured out the moles in that 1.89 gram C2O4. Now, what I can do is I can, what they've done is they've also, for the same solution that we prepared, he does a titration and he figures out the concentration of the solution A, the H+1 concentration. Now, using that H+1 concentration, what we can also do is, I mean, we've got the concentration. So we can find the moles of H+1 in 250 cm3. The volume, so volume is 250 cm3. So that's volume times concentration. The concentration is already given to us. So that's going to be 6.1 times 10 power minus 2. So here's what I'm trying to do. Since it was the same solution A, which we prepared 1.89 grams A, we knew the moles of C2O4 ions based on the titration that we did. And we also know the concentration of H+1 in the same solution. Using that concentration, I'm multiplying it by the volume of the solution to figure out how many moles of H+1 I've got. So can anyone tell me what these moles are?
Zero point zero one five two five.
0.01525?
25. Mm-hmm.
So in our 250 cm3 solution that we had, H+1 is these many moles, right? And C2O4 2 minus are like, this is going to be what? 0.0122, right? So what's the simplest whole number ratio like between the two? Like divide both of them by the smallest. What do we get if I divide them by the smallest?
Four is to five ratio.
Do you 4:5? So we're getting 4:5. So that means in the formula, the C2O4 and H ratio is 4:5, right? So that's the ratio. So we need to find the ratio between C and B. 4:5 is 1:1.25, right? I mean, look at the formula, that's H ratio and C2O4 ratio. So we were able to figure that out, right? So 4:5. So that means if I write the formula, like this is C2O4. So you said that there were 4 of them. And H is B, right? So that there's going to be 5 of H, right? And then you've got potassium as well, and you've got D as well. You've got water molecules as well. So how would you find A then, the value of A? I mean, B and C ratio was fine. We were able to figure that out. How would you find the value of K? That's the question now. How would you find A? Okay, one way to find K is I mean, for this you would have to like understand what I'm just trying to figure out if there's a mathematical or a moles way of doing this, but the mathematical way of doing that was that he had initially stated, yeah, I don't think A is going to be 1. A is definitely not going to be 1. What A is going to be that, see, where is the H plus 1 coming from? This H plus 1 in the formula, that's all coming from the ethane dioic acid, right? Because if you go back and look at the question initially, this is where we started off. There was this ethane dioic acid and that got neutralized by KOH partially. So some of the H plus 1 got knocked out and they got replaced by K, some of them. So if all the H plus 1 get knocked out, they're going to be replaced by K. So I need to figure out that. How many H plus 1 did this thing have initially? There were 8 H plus 1, right? Like one molecule will have, there's going to be an H plus 1 here, there's going to be an H plus 1 here. So that's, if you have 4 of them, so in total there would be 8 H plus 1, right? Initially. But in the formula, you're just left with 5 now. So that means there are at least 3 K plus 1 that have now replaced a few of the H plus 1 ions. I mean, is that clear that initially there were 8 H plus 1 ions with ethane dioic acid, but when partial neutralization happened, there's still 5 H plus 1 ions, but now you've got 3 of them have been replaced by K plus 1. Is this idea clear?
Yes, sir.
So A over here is going to be 4:5 ratio, and this is going to be ratio 3. So if you compare it with 4, that's the value of A, because I think he's taken one of them as ratio 1 because he's dealing with ratios. He's not talking about the actual number. So it's 4:5 ratio 3. So if this is 1, this comes out to be 1.25, then 3 will come out to be 0.75 if one of the ratio is taken as 1. So A is going to be 0.75. Is this part clear?
Sir, can you scroll a bit up? Sir, वो जिधर उन्होंने आंसर दिया होता है कि if you cannot find your answer, use this value. So is it a wise option that we always use that value in case we get our answer wrong?
नहीं,
जिस
you
तरह
can
इधर उन्होंने दिया 1.18 into 10 to the minus 2.
नहीं, उसमें if you're unable to calculate, तो हमने तो calculate कर लिया था.
हाँ, लेकिन कभी-कभी अगर गलत इस तरह आ जाए,
नहीं, फिर अगर डाउट
फिर
में हो गए ना, अगर तो पता ही नहीं, समझ नहीं आएगा पहले क्या हुआ है, फिर तो डेफिनेटली गो फॉर दिस वन. ठीक है. अच्छा, लेकिन दिस पार्ट इज एक्चुअली वेरी डिफिकल्ट, दिस वन, क्योंकि इट्स trying to, I mean, this one, I mean, this question, especially this section over here. The previous part was not that difficult. Finding moles, that's not an issue, but understanding how the salt is partially getting neutralized. Where's the salt? Salt over here. H plus ones are getting knocked out and they're getting replaced by K plus 1. We were able to figure out that there was a certain ratio of C2O4 ions and H plus 1. We were able to figure out that the mole ratio came out to be 4:5. We had to figure out, so what is the value of K? So we had to, now that part was pretty tricky. That was pretty tricky. That you had C2O4, it was supposed to have 8 H plus 1s. But since in the formula now you've just got 5, so that means 3 of them got neutralized and they got replaced by K, and there's going to be 3K. Jivey, kaun sa part? Ye K wala? The question started right at the beginning. The question started that there was ethane dioic acid, right? And it was getting neutralized, but he said that it was getting partially neutralized. It's a carboxylic acid. So whenever it gets neutralized, the amount of H decreases and the amount of K plus 1 increases, right? If this H plus 1 gets neutralized, the amount of H plus 1 will decrease and the amount of K plus 1 will go up. So basically, this is what's happening. You have an ethane dioic acid, and every ethane dioic acid has 2 H plus 1 ions, and every time it gets neutralized, the amount of H decreases and the amount of K increases. But is this part clear, this thing? How you can relate this to this thing? Is that clear? I said, now in our question, we did the same reaction, but we separately found out कि C2O4 के जो moles are in the formula, we found out that its moles are, I mean, the ratio we found out was, iske 4 like this was 4, right? Yep. So we separately found out that there were 4 moles of C2O4. And he did 2 reactions. He did another reaction with H plus 1, and we separately found out that H plus 1 moles are 5. Okay. So the same substance separately reacted with 2 things. We were able to figure out the moles of C2O4. We were separately able to figure out the moles of H plus 1. Now bring them together. If you have 4 moles of this thing, so how many H plus 1 should there be in the formula? There should be 8 H plus 1. Like if it did not get neutralized, there should have been 8 H plus 1 ions, right? I mean, there should have been 8 H plus 1 ions. But in the reaction, we found out that you don't have 8 H plus 1. You actually have 5 H plus 1 ions. So that means 3 of the H plus 1 got neutralized, right? And they got replaced by K plus 1 ions. Is this idea clear? And the whole number ratio was 1. This is 1.25. This is 0.75. Okay, that's how you were able to figure this out. So okay, we'll probably go through this question, the last parts once more. Okay, abhi the time we're out of time. Okay, so iska baki na try and go through the rest if you can. I mean, we're actually at the end, by the way, so we can kind of figure this out. That we can figure out the mass of 1 mole. That's probably not. We found K. You found B, so you should be able to figure out D as well then, because the total mass is 1.89 grams. So I think you should be able to do that. So we don't have time to analyze this. In the next class, we'll probably redo some of the parts. TK. Try going through the last 2 parts as well. Okay, everyone.
Yes.